Today, I'm going to derive a relation between the expectation value of position, time derivative of expectation value of position, and time derivative of expectation value of momentum. That is known as Ehrenfest theorem. Actually, this is the quantum mechanical analog of Newton's second law. By deriving this relation, we are tracing back the Newton's second law of motion, which is one of the fundamental relation in physics. So, in previous classes, we have learned two different perspectives. That is one a perspective about operators and statecuts. That is mainly operators. That is one is Heisenberg's picture, and another one is Schrodinger's picture. Okay, to be able to solve the equation of motion quantum mechanics, actually we need to construct a Hamiltonian. How we will construct a Hamiltonian? For a physical system with a classical analogus, we assume Hamiltonian to be the same form as in classical physics. Okay, that is in classical physics, the position will be there, position xi will be there, then momentum pi will be there, and we are merely replacing this position and momentum with the position operator and momentum operator. Okay, in that way we are constructing the Hamiltonian. Okay, one condition is Hamiltonian should be Hermitian in quantum mechanics. So we have to rearrange the form of position and momentum in classical mechanics. That should be a Hermitian. Okay. So if a physical system without classical analogus, actually we assume some Hamiltonian, and that we need to solve the equation of motion, and after that should be agree with the empirical results. Okay, so before going to derive these relations, I'm introducing you two useful formulas. That is xi f of p, that is function of momentum equal to ih cross dou f over dou pi. And another one is this is f of p is function of momentum, and the commutator of this is commutator of xi and f of p, and this is commutator of pi and g of x. G of fx is the function of position. Function of position operator. Okay, and that is equal to minus ih cross dou g over dou xi. Actually, this equation we can solve through quantum mechanics itself, but now I'm saying how to solve this equation. We can use a classical we can use this analogy between the quantum mechanics and the quantum mechanical commutator bracket and the classical mechanical Poisson brackets. Okay, we have actually discussed this relation, commutator bracket over ih cross in classical mechanics, that is the Poisson bracket. So we know how to solve the Poisson brackets. We know how to use the Poisson brackets. That is, if we are taking xi f of p function of momentum, that is equal to dou xi over dou xi, dou f by over dou pi minus dou xi over dou pi into dou of p over dou xi. Okay, that is equal to dou this we will get 1, and this term will be 0. So we will get dou f over dou p divided by dou pi into this is classical mechanical Poisson brackets results, and when we are multiplying with ih cross, then this will be quantum mechanical result, quantum mechanical commutator relation. Okay, that I have used it here, and this also where f and g are functions that can be expanded in powers of pj's and xj's respectively. Okay, this pj's and xj's or pi or xi means x, y, z as well as px, py, px, py, pz. Okay, so we are going to consider free particles. For free particles, we need to make equation of motion for that one, that we are taking Hamiltonian of the same form as the classical mechanics. For free particle in classical mechanics, that is Hamiltonian is h equal to p square over 2m. Okay, that itself we are taking as the Hamiltonian operator in quantum mechanics, that is equal to px square plus py square plus pz square over 2m, where pi, xi are the momentum position operators in the Heisenberg's picture. Okay, we are not writing the superscript as Heisenberg's picture. This is actually pi square is pi in Hamiltonian, because we have derived an equation of motion in Hamiltonian picture. Okay, so here we are taking momentum as well as position in Hamiltonian picture. Actually, we are skipping this skipping of writing this superscript for simplicity. That's PAXA, moment and position operator in Heisenberg's picture. And if you have to write this relation, that is dA over A is operator in Heisenberg's picture, or dt equal to, or time derivative of this operator is equal to 1 over h cross commutator of A comma h, where A is the operator in Heisenberg's picture. Okay, if we are taking the operator as the momentum, then we will get dpi over dt equal to 1 over h cross pi h. Okay, I'm skipping this superscript h. This is in Heisenberg's picture, keep it in mind. 1 over h cross pi h. Okay, and that is equal to 0. When we are considering this commutator of pi and h, just look at this. H is the function of momentum. Okay, px, py, pz. And here it's pi. That means pi means it may be px or py or pz. And we know this momentum and commutator of momentums, that is pi. If instead of h, it will come px square plus py square plus pz square. Both are the function of momentum, and then this will be equal to 0. Okay. So if you need more explanation, for example, let me take pi as px. Okay, pi as px, that means dpx over dt equal to 1 over h cross commutator of pxh. Commutator of pxh, that is equal to 1 over h cross px square plus py square plus pz square over 2m, and we can take this 2m outside, that is 1 over h cross 2m. This we can explain as commutator of px square plus commutator of px py square plus commutator of pz commutator of pz square. And we have learned pi pj equal to 0, so finally we will get this will be equal to 0. That means if dpi over dt equal to 0, then p will be the constant of motion. Okay, p will be the constant, pi will be the constant. This is for a free particle. The momentum operator is constant of motion. Okay, we have considered about the situation about free particle, and for free particle the momentum operator is a constant of motion, which means that pi of t equal to pi of 0 at all times. Okay, that means momentum will not change with respect to time. So we can mention generally from Heisenberg's equation of motion, whenever an operator A commutes with the Hamiltonian, then AH is a constant of motion. Here P is commutes with the Hamiltonian. Here look at this. Here in this equation, P is commutes with the Hamiltonian. So Pi is commutes with the Hamiltonian. So P is the constant of motion. That means momentum will not change with respect to time. Okay. Next we will consider the position operator. Okay. A position operator, rate of change of position operator, or time derivative of position operator, that is dxi over dt. That is dxi over dt equal to 1 over h cross commutator of xih. That is equal to 1 over ih cross 2m xi px square plus py square plus pz square, and that is equal to 1 over ih cross 2m into ih cross dou by dou pi of function of p. Okay, here I am using this identity. This is the function of this. Let me say this equation 1 and this equation 2. So h is a function of p, and I am using this equation 1, xif of p, ih cross dou over dou pi. Okay, that identity I am using here. So that is ih cross dou by dou pi of the function of momentum. Okay, that is function of momentum. This IH cross and IH cross will get cancelled. 1 over 2m into 2pi. Okay, if this is px, then py pz, the derivative differential of pi pz will be equal to 0, and px only, the px square, derivative of px square exists. That means if we are differentiating with the dou by dou px of dou over dou px of px square equal to 2px. Okay, if it's py, then we will get if this pa is py, then we will get 2py. If this pa is pz, then we will get 2pz. So generally I can say that 2pi. So 1 over 2m into 2pi equal to pi over m, and that is equal to, actually we have earlier solved that pi will not change with respect to time, momentum will not change with respect to time. So I can say that pi of 0, this is equal to pi of 0 over m. Okay. Okay, that is, we got dxi over dt equal to pi of 0 over m. So let me derive this equation for xi of t equal to, let me integrate pi of 0 over m dt. Okay, that is equal to pi of 0 over m t plus a constant. Then we have to apply the initial conditions to find out the constant at time t equal to 0, xi of 0. Okay, look at this. Xi of 0, that means t equal to 0, that is equal to c. So xi of 0 equal to c, that means we can rewrite this equation xi of t equal to pi of 0 over m t plus xi of 0. Okay, that means xi of t position, xi of t position operator at time t equal to position operator at a time 0 plus momentum operator over m into t. Okay, what this equation resemble? This is the this equation which is reminiscent of the classical trajectory equation for the uniform rectilinear motion. Okay, this is a uniform rectilinear motion, equation of uniform rectilinear motion. Okay, this will come, look at this, xi minus xi of t minus xi of 0, xi of t minus xi of 0. If I am saying, if I am taking a classical mechanical situation, this is the position at time t, this is the position at time t equal to 0, that is equal to p over m. P over p means, look at this, p is mass into velocity, over m means m and m will get cancelled, and this is velocity into time. Okay, so this I can write velocity into time. That means displacement equal to velocity into time. This is an example of a body, of an object moving with a constant velocity. If we need to find out the position at a time t equal to 0, we can use this equation. So this is the equation for uniform rectilinear motion in classical physics. Okay, and look at one important point. Even at even though we have xi0 xj equal to 0, that means at equal times, the equal times commutator of position bracket will vanish. The commutator of xi at different times does not vanish. If we are taking the commutator of position different times, that is xi of t, xi of 0, that is equal to pi of 0 t over m xi of 0. I am taking this term only because xi of t is xi of 0 plus pi of 0 over m into t. Okay, but I am taking, even if I take this term is completely pi of 0 t over m plus xi of 0, the second term xi of 0, xi of 0 and xi of 0 will get vanished. That's why I had taken this term only. This will not get vanished. So that is equal to T over M Pi of 0 Xi of 0, that is equal to T over M into IH cross. Okay, commutator of Px is minus IH cross equal to minus IH cross T over M. That means at different times this position operators will not commute. Okay. When our consideration is Heisenberg's uncertainty relation, Heisenberg's uncertainty relation is this one. Delta I whole square into delta B whole square, expectation value of delta whole square into delta B whole square greater than or equal to 1 by 1 over 4 mod AB whole square, commutator of AB whole square. So here we are taking as one operator as delta xi square, expectation of delta is xi square at a time t, and then another operator is delta xi square at a time t equal to 0. Okay, that should be greater than or equal to 1 over 4 mod of xi of t xi of 0 whole square, that is greater than or equal to we have solved here the commutator of xi at t and xi at t and xi of 0 minus iht over m. Okay, so minus iht over m whole square greater than or equal to 1 over 4. This is actually mod c square is c star c. So here c star is IH cross t over m into minus IHT over m, that is greater than or equal to 1 over 4 h bar square t square over m square greater than or equal to h bar square t square over 4 m square. Okay. This relation implies that even if the particle is well localized at t equal to 0, its position becomes more and more uncertain with time. At a particular time, this object is well localized. We can we can find out the position at a particular point, specific point, and then by the time being, the position of this particle will be uncertain. Okay, it becomes more and more uncertain with time. Okay. We now add a potential V of x to our earlier free particle Hamiltonian. Okay, earlier we had taken it was a free particle h equal to p square over 2m, that was the Hamiltonian. Now we are adding a potential term V of x. So V of x is a function of x by z operators. Okay. And once again we will do the same operations, that is dpi over dt equal to 1 over h cross pi vx v of x. Okay, pi v of x like a dA by dA over dt equal to 1 over h cross ah, and this equation we are using here, and that is equal to 1 over h cross into minus ih cross dou over dou xi v of x by equation 2. Okay, that's we are using equation 2 here. Equation 2 was this one, pi g of x equal to minus ih cross dou g by dou xi. Okay, we are using that equation 1. Equation 2, that's equal to this ih cross will get cancelled and we'll get minus dou or dou v over dou xi. Okay, let me put this as equation 4, and next again we are finding dxi over dt, that is equal to pi over m. I'll explain how to find it. dxi over dt equal to 1 over h cross xi h. This is our usual equation. That is equal to 1 over h cross h Hamiltonian is p square over 2m plus v of x, and this we can write as xi p square over 2m plus xi v of x, and this will get 0. This is equal to 0 because this is a function of x. The x and function of x will commute, and that will become 0. Okay, so the remaining term is xi p square, and that is equal to xi px square plus py square plus pz square. Xi means x, y, or z. Okay, that is 1 over ih cross 2m xi pi square, and that is equal to 1 over ih cross 2m into this is xi pi square is ih cross 2 pi equal to pi over m. Okay, this is equation 5. Now we can use Heisenberg equation of motion to deduce Heisenberg equation of motion we are using. Heisenberg's equation of motion, this one dA over dt equal to 1 over h cross ah. Okay. Instead of that operator a, we are taking dxi over dt equal to d square xi over dt square equal to 1 over ih cross 1 over ih cross 1 over ih cross ah. Okay, instead of a, here this is the operator dxi over dt, so dxi over dt h, and that is equal to 1 over h cross pi over m h, because dxi over dt is pi over m and h, that is equal to 1 over h cross pi over m p square by 2m plus v of x, that is equal to 1 over h cross pi over m v of x. Okay, because the first term is pi over m comma pi over 2m, so this both are functions of momentum, so we will get, this will get commute, and the remaining term, the term only which remains is pi over m v of x. Okay, so this will lead to equation that is 1 over ih cross m into this is pi v of x, again we are using equation 2, that is minus ih cross dou by dou xi of bx, that is d square x over dt square equal to minus 1 over m dou by dou xi of b of x, and this is equal to dou v over dou vx over dou xi is dou vx over dou xi is dou xi is minus dp over dt. Okay, so this minus sign and minus sign will get cancelled, 1 over m dpi by dt, that is equal to, if we are taking this m into left side of this equation, we will get m d square x over dt square equal to dpi over dt. Okay, this is rate of change of momentum, that is force. I'm saying the classical analog, actually this is the operator, so I'm just comparing this with the classical mechanics. This is in the dimension of force dpa over dt, and this is in the dimension of mass into acceleration, that is equal to F equal to ma. F equal to ma is our Newton's second law, which is the one of the most fundamental law in physics we have derived till we have got the quantum mechanical equation analogous to this one. That quantum mechanical equation is, that is equal to this m we can take, I'll leave this one, this m we can take left side, take into left side, that is m d square x over dt square equal to minus del v of x. Okay, minus del v of x. This is the quantum mechanical analog of Newton's second law. By taking the expectation values of both sides with respect to a Heisenberg state get that does not move with time, we obtain. Okay, we are taking the expectation value of both sides. That means we will get m into d square over dt square. Expectation value of x equal to d over dt. Expectation value of p equal to minus expectation value of del v of x. This is known as Ehrenfest theorem. Okay. Why we are taking this expectation value is actually, when we are taking the expectation values, it doesn't matter whether we are examining this through Heisenberg's picture or Schrodinger's picture, because whenever the expectation value takes, it doesn't matter whether it's Heisenberg's picture or Schrodinger picture. Expectation value of both pictures will be equal to, when we are considering this equation, we need to take the Heisenberg's picture. We need to consider the Heisenberg's operators, the operators in Heisenberg's picture. But when we are taking the expectation value, we don't need to consider the Heisenberg's picture. We don't need to bother about whether it's Heisenberg's picture or Schrodinger's picture. We can take simply the expectation value of this one. Both are equal. Okay, this is known as Ehrenfest theorem. So we have solved the quantum mechanical analog of Newton's second law. Okay, all right. Another important point which we need to note here is actually the Planck's constant h cross have completely disappeared. It is we need to understand that this means the center of the wave packet moves like a classical particle subjected to a potential v of x. Okay, the center of the wave packet moves like a classical particle. Actually, this Planck's constant is differentiating the quantum world and classical world, and here it's completely disappeared. It's missing in this equation. Okay, so that means the center of the wave packet moves like a classical particle. Okay,